So in this video, I'll try to promise to upload it because I've done lots of videos, tons of ones for real, and I did not upload any one. I'm not sure why, but I'll try my best, especially that Unit 1 exam is like in a couple of days. It's on 6th of May, I guess. So we have 9 days to go. Let's get started with the Unit 1 revision, and I'll try my best also to have Unit 1 past paper solving for physics AQA Oxford, the international code, the 9620. So what do we know about Oxford? No, yes, this one. What do we have in Unit 1? Basically, we do have those units, those chapters exactly. Measurements and their errors, mechanics and materials, particles, radiation and their radioactivity. So starting with one of the first chapters, measurements and their errors, basically we will be studying it from two different places. Starting with here, let's just know the points, etc. We have the use of the SI units and their prefixes, limitation of physical measurements, and the estimation of the physical quantities. So there isn't much to learn from here, so we'll be going directly into here. So this is just a quick revision. In case you want actually explanation, not this one, you can go for the detailed notes. We might be using it for some chapters. Also, there are other types of notes for the international AQA down in PMT as well. So let's get started with the SI base units with Igcse.science.notesz Z. The base units are the set of 7 units of measure from which all other SI units can be derived. The ones you need to know are the mass, which is in kilograms, the length, which is in meter, the time, which is in second, the current, which is in amperes, and the temperature, which is in Kelvin, and last thing, the amount of substance, which is in mole, but we're going to use this more into the A2 part. All other units can be expressed in terms of the base units. For example, 1 joules is equal to 1 kilogram meter square times second to the power of -2. 1 volt can be calculated using 1 kilogram meter second, etc. What does that look like? Basically, it looks like that. For example, here the joules, so we have the kilogram, so this is mass. So 1 joule is equal to mass times length square, so basically the area, times the T. So when you do all that with a special way, of course, like, shouldn't be this way, you get to joules. For example, when you say, we'll be seeing, we'll see, but like, for example, force is equal to MA, right? So we have A, which is in kilograms, and then you have the MS to the power of 1, and then this is equal to the Newton, So it can all be derived into something from the base units. Okay. Unit prefixes. You should and put under should some underlines. Maybe if it's your first time studying this, you're just gonna skip this part. But you should be used. Prefixes should be used when stating values to avoid the use of large amounts of notes and standard terms, and you should need to know the following prefixes. This is a must, guys. Tera is 10 to the power of 12, giga is 10 to the power of 9, mega is 10 to the power of 6, kilo is 10 to the power of 3, centi is 10 to the power of -2, milli is 10 to the power of -3, micro 10 to the power of -6, nano 10 to the power of -9, pico 10 to the power of -12, and femto 10 to the power of -15. You can convert between prefixes and standard form. For example, the 620 nanometer, here we have the nano, it's basically 10 to the power of -19, so it will be 620 times 10 to the power of -9 meter, okay, which is equal to 6.20 times 10 to the power of -7. Then we go to the significant figures. Now, the significant figures is such an important thing also to know because it's usually 1 mark from each question. Your calculated quantities should be given to the same number of significant figures as the value with the least number of significant figures using the calculation. In tables, data should be written to the same number of significant figures. However, when crossing multiples of 10, the same number of decimal places should be used to avoid changing the accuracy. This number of decimal places of the logarithm of a value should be the same as the number of significant figures as the value. For example, length 60 should be quoted as 4.09. Experimental key terms, we have the random error, the systematic error, and basically that the random errors, the measurements vary due to unpredictable circumstances. They cannot be corrected and can only be mitigated by making more measurements and calculating a new mean. Now we have the systematic error. Measurements differ from the true value by a consistent amount each time. They can be corrected by using a different technique to take measurements. Now we have the precision, how close measurements are to each other, and the mean. Now that we have the accuracy, how close a measurement is to the true value. Then we have the repeatable, when the original experiment repeats the investigation using the same method and equipment and obtains the same result. It's, in terms of sociology, it's reliable. Reproducible, when somebody else repeats the investigation or the investigation is performed using different equipment or techniques and the same results are obtained. Let's say resolution, the smallest change in a quantity being measured that gives a perceptible change in the reading. Finding uncertainties. This is such an important chapter as well. I really loved skipping it, but it's very important to study. The uncertainty of a result is the interval within which the true value can be expected to lie. Again, the uncertainty of a result is the interval within which the true value can be expected to lie. The absolute uncertainty of a reading is no smaller than plus or minus half of the smallest division. The absolute uncertainty of a measure where two judgments are required, for example, measuring a length using a ruler, is twice this. For multiple readings, the absolute uncertainty is half the range. Absolute uncertainties have the same unit as the quantity. And we have the fractional uncertainty, which is the absolute uncertainty divided by the measured value of multiple readings divided by the mean. The percentage uncertainty is the fractional uncertainty multiplied by 100. Fractional and percentage uncertainties have no units. Pardon. I want also to go for having uncertainty. Why am I stopping? Apart from the other notes. But before we go, let's just say that when adding or subtracting data with uncertainties, add the absolute uncertainty. When multiplying or dividing data with uncertainties, add the percentage uncertainty. When raising data with an uncertainty to a power, multiply the percentage uncertainty by that power. When multiplying data with an uncertainty by a constant, multiply the absolute uncertainty by that constant, but not the percentage uncertainty. Here, uncertainties in graphs. The uncertainty in a data point on a graph can be represented using error bars. Two lines of best fit should be drawn on the graph. The best line of best fit, which passes as close to the points as possible, and the worst line of best fit, either the steepest possible or the shallowest possible line, which fits within all the error bars. The percentage uncertainty in the gradient and y-intercept can be found from the equation below. For the percentage uncertainty, you can do best gradient minus worst gradient over the best gradient times 100, or you can say percentage uncertainty is equal to best y-intercept over worst y-intercept over the best y-intercept times 100. Let me just go for 1 second in the detailed notes for the uncertainties part because it's actually important. Please, where are you? Here. So guys, the uncertainty of a measurement is the bounds in which the accurate value can be expected to lie. For example, 20 cc plus or minus 2 cc. So the true value can be between 18, which is basically 20 minus 2, 18, or plus 2, which is 22 cc. The absolute uncertainty, which gives us a fixed quantity, like 7 plus or minus 0.6, or as a fraction, for example, 7 plus or minus 3 over 35, or as a percentage, 7 plus or minus 8.6%. And to reduce percentage and fractional uncertainty, you can measure larger quantities. Also, you have something called resolution and uncertainty. Readings are when one value is found. For example, reading a thermometer. Measurements are when the difference between two readings is found. For example, a ruler, as both the starting point and end point are judged. And the uncertainty in a reading is plus or minus half the smallest division. For example, the smallest division is 1 cc in a thermometer, so it's plus or minus 0.5, as 1 divide 2 is 0.5, so it's plus or minus 1.5, or whatever. The uncertainty in a measurement is at least plus or minus 1 smallest division. For example, a ruler must include both the uncertainty for the start and the end value. As each end has plus or minus 0.5 millimeter, they are added, so the uncertainty in the measurement is plus or minus 1 millimeter. Guys, digital readings and given values will either have the uncertainty quoted or assumed to be plus or minus the last significant digit. For example, 3.2 plus 0.1 volt, the resolution of an instrument affects its uncertainty. For repeated data, the uncertainty is half the range. Largest minus smallest value show as mean plus or minus range over 2. Guys, you can reduce the uncertainty by fixing one end of a ruler as only the uncertainty in one reading is included. You can also reduce uncertainty by measuring multiple instances. For example, to find the time for one swing of pendulum by measuring the time for 10 giving, for example. So you do 6.2 plus or minus 0.1 second. The time for one swing is 0.62 plus 1 or 0.1 second. The uncertainty is also divided by 10. Uncertainties should be given to the same number of significant figures as the data, combining them. So we said adding or subtracting, add the absolute. Multiplying or dividing, add the percentage. Raising to power, multiply the percentage uncertainty by power, as you see over here. So we have the radius of a circle is 5 plus or minus 0.3 centimeter. What is the percentage uncertainty in the area of the circle? Pi times 25 gives us 78.5 centimeters square, and this is the area. So percentage uncertainty in radius 0.3 over 5, which is basically this times the 100, giving 6%. And then we do 6 times 2, which is the power in the r square, which is 12%. So then you do 78.5 plus or minus 12%. Last but not least, the uncertainties in graphs. The uncertainties are shown as error bars on graphs. For example, if the uncertainty is 5 millimeter, they have 5 squares of error bar on either side of the point. A line of best fit on a graph should go through all errors. Last rule that wasn't mentioned there, the percentage uncertainty is equal to maximum gradient minus minimum gradient over 2. Guys, we need a break from the uncertainties that I've been saying for the last hour. Anyways, it wasn't an hour or anything. So finally, we're done with this thing. Let's go to the physical quantities, but after a minute break. Okay, I wished for more break, but we're back. Estimation of physical quantities. You can estimate the order of magnitude of physical quantities. For example, include the radius of proton, which is 10 to the power of negative 50 meter. Radius of atom, 10 to the power of negative 10 meter. A height of a human, 10 to the power of 0 meter. Huh? Oh, 0. Pardon. Like, someone 10 meters long? 10 to the power of 0. Guys, a rule not to be like, whatever. 10 to the power of 0. Why would the height of a human be 10 to the power of 0? Like, 1 meter. Who's 1 meter? Who is 1 meter? I know it's an estimate, but like, who is 1 meter? Anyways, how long is 1 meter? Oh, 1 meter is actually long. Guys, don't talk with me about measurements. Did you know now why I've been skipping like whatever? 1 meter is actually long. I hate this. Like, I hate physical quantities, or like, not physical quantities. I hate when you do like measurements. Like, why do I care? Like, a person is that long. Is that long? Oh, 1 meter is actually long. I'm sorry, guys. Radius of Earth itself is 10 to the power of 7. And I'm saying why a height of human is 10 to the power of 0. Guys, I'm sorry. No, I'm actually sorry. Okay. That's the last slide. Finally. I don't like... I'm not gonna say I really hate this chapter. It's mostly easy. Like, you see from the grade threshold, for example, beside the January 25 boundaries were very high for, I don't know why. But, for example, let's see here, like, this unit of the uncertainties, tough and measurements and things have the lowest grade boundary. So you can get a high A star there. Not a high, like a normal, easy A star. 52. So it's a good chapter, you know. It's not that hard. Like, it's an easy... I'm not sure what to say, but like, I want to support you guys, so get supported. Have a nice day. We're not done yet. Anyways. So we're done with the measurements and their errors so far. I'll just go through the... Do we need to know anything? We've done on everything. Just get this, guys, as a... what is it called? Oh my god. As a checklist to make sure you know it. So basically, I'm just gonna convert something. I don't like rulers. I don't like measuring things with that millimeter, etc. Guys, I'm shocked. Like, I'm saying why a human could be 10 to the power of 0 meter and the earth radius is 10 to the power of 7. Because you're just a human, after all. Okay. Let's get started with mechanics and materials. Scalars, vectors, moments, motion along a straight line, projection motion, Newton's laws of motion, momentum, work energy and power, conservation of energy, bulk properties of solids, and the Young model. This should be covered today, inshallah. I want to tell you something, guys. This is an easy chapter. No matter if you loved it earlier or you didn't, but it's an easy chapter after all. Like, let me tell you something. Scalars, for example, is something like speed, which only have magnitude. Vector is something like velocity, which has both magnitude and direction. How to memorize something like that? As here, for scalar is basically the same as for speed, which is basically the same as for mass. So here you have two examples already. Now, velocity is vector is the same v for velocity, and you see they're all harsh, like force and displacement. Here, speed looks like time and distance. So just do some colors. You're gonna find everything is easy. I hope so. So let's go directly into studying now. I want you guys to come with me to the mechanics and materials. Where is it? Let's get started. What do you know about drawing vectors? So we said, what do you know even about vectors? Vectors have both magnitude and direction, and such as velocity and force. Compared to scalar quantities, which only have a magnitude, such as mass, distance, and energy as well. Vectors can be shown with arrow drawings, as they have direction. If they are drawn to scale, then they can be physically measured. If not, math must be used. Here, for example, if you have 12 and 5 and you want to find the resultant vectors, just do Pythagoras. I'll tell you the rule now. And then here's the drawing thing. Vector triangles can determine whether the forces are balanced and with a resultant force of 0 Newton, or this is called resultant, or not. This is called the resultant vector. Beside the resultant vector, I just want to tell you the Pythagoras rule. If you have a straight line, if you have a straight line that looks something like a right angle triangle that looks something like that. Okay, that looks something like that. Just want to tell you that the most loved is the blue one, because this is called hypotenuse. If you call this X and you call this X, no one really cares. If you call this P and you call this P, no one cares. If you call this H, no, that's H. If you call this blah 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 and this is blah blah blah, no one really cares. They're just the same thing. Since H is the favored, H is alone at the side because it's the boss. So you put H square and then a big equal signs that says that those, whatever what you're gonna call them, I myself call them P and B because it doesn't really matter, is equal to P square plus B square. Alright. I'm not sharing anyone. Okay. Resolving the vectors. Resolving a vector means splitting it up into horizontal and vertical components. Because horizontal and vertical meet at right angles, they can be calculated using trigonometry. However, they can also be drawn to scale and found using the parallelogram method. The key to resolving vectors is putting the vector head to tail. the vertical component y, and the horizontal component x, as you see over here. Moments. Just give us a moment. Ooh, let's go, baby. The moment of a force about a point is the product of the force and the distance from its line of action to that point. Moment nm is equal to force n times perpendicular distance m. Where an object is in equilibrium, the moment on it about a point are balanced, for example, around a car's wheel axle, and you can use this to work out forces and distances because total clockwise moment is equal to total anti-clockwise moment. A couple is a pair of equal and opposite parallel forces acting on the body that do not act in the same line. Moment of a couple nm is equal to force n times perpendicular distance between lines of action m. Center of mass. Center of mass is where the mass of an object can be considered to be concentrated, but guys, this is later to know. Let's just go to Newton's law of motion. So there are 3 laws because Newton, our guy, had many laws. First of all, the velocity of an object will not change unless a resultant force acts upon it. Second law is that F is equal to ma, where force in Newton equals mass in kilograms times the acceleration in meter per second, -2. My bad, guys, when I explained at the beginning, it's mass to the power of -2. Newton's third law, every force has an equal and opposite force. And if you're Arab, every كل فعل له رد فعل, which means كل فعل له رد فعل, which means that every action has a reaction, like has an equal reaction, has a every force has an equal and opposite force. That's it. But فعل means like reaction and action. Okay. The Sovat and projectiles. Guys, S is displacement, U is the initial velocity, V is the final velocity, and A is the acceleration, and T is time. Before we go to the projectiles, or after, before, let us just go to the syllabus thing. So we're done with the moments and the scalars and vectors. Oh, so it has the center of mass. So we're going to go back to the center of mass. But before we do, let's just go do the displacement, speed, velocity, and acceleration. You gotta know that V is equal to delta S over delta T. Or in other words, A is equal to delta V over delta T. And here we have the equations for the uniform acceleration, which goes under the Sovat thing. We have 4 rules. First of all is the V equal U plus AT, which is the same as A is equal to V minus U over T. Then we have the S equals V plus U over 2 times T. Then we have S equals UT plus half AT square. S stands for displacement. Then we have V square equal U square plus 2AS. And this is the only rule that doesn't have time. If we go from the other way around, first rule doesn't have, what is it called? First rule is the only rule that doesn't have displacement. Second rule is the only rule that doesn't have acceleration, but you have U, V, and T, so you have acceleration in your mind, like whatever. Third rule, you have everything but V, but you still have A, and T, and U, so you can get them. Then last rule, you have V square, U square plus 2A as the only rule that you don't have T, but you have V and U, so you can get the A. Guys, this is just like, but like, it's not always the case, so yeah. Acceleration due to gravity is the G, which is 9.81. So calculations may include average and instant speed and velocities, representation by graphical methods of uniform and non-uniform acceleration, for example, method of a bouncing ball. Let's go again to the notes. I hope I got that. I'm always getting that. So let's just, no, I want the, mate. I want the center of mass. Okay. So what's the center of mass? Center of mass is where the mass of an object can be considered to be concentrated. The line of action acts from the center of mass and shows how gravity is acting upon the object. The center of mass can be found by suspending an object by a pin and then using a plumb line to draw on the line of action where they cross in the center of mass. If the line of action falls outside of the width of the base, then the object will topple. Okay, so here are the lastly, guys, I'm sorry. Okay, I should be calmer. So Sovat, I told you the rules. So in projectile motion, the horizontal and the vertical components are treated separately. Acceleration is due to gravity, hence only affects the vertical component and is positive if acting with the object, and negative. Guys, I hate answers. If acting, that was a random fact, I don't know. And negative if against it. So, lift, drag, and terminal velocity. Friction is a force that opposes motion when moving on a solid. Drag is a force that opposes motion in a fluid. It usually increases with speed. Lift is an upward force created on an object as it moves through a fluid due to the shape of an object. Terminal velocity happens when fractional displacement forces equal the driving forces, causing equilibrium and zero acceleration. Now we have momentum and kinetic energy. Momentum, guys, I love them for no reason, for real. Like, they're very toxic, but like, I like them. So I want you to be alert. Let's go. In a closed system, momentum is conserved. This means that the product of velocity and mass must be the same before and after, which occurs in both collisions and explosions. So P is the momentum. So P1 is equal to P2, which means momentum before anything is equal to momentum after anything, as the momentum is conserved. How do you calculate momentum? P is equal to M times V, where M is the mass in kilograms and V is the velocity. So here M1V1, the mass and the velocity of object before is equal to the mass and of a velocity after of like different two objects, because the mass also doesn't change, right? So in an inelastic collision, kinetic energy is not conserved. This means we can work out the change in kinetic energy and hence how much energy dissipated into other forms. The kinetic energy is calculated as half mv squared. So delta Ek is equal to Ek final minus Ek initial. In an elastic collision, kinetic energy is conserved, which means we can work out the kinetic energy before and after given similar pieces of information. If Ek final is equal Ek initial. The impulse, guys. What is the impulse? Impulse is the change in momentum, right? So it's basically that it's delta mv. But let's also have another thing where you can say F is equal to ma, F is equal to delta mv over delta t, as A is equal to delta v over delta t. And then so F delta t is equal to delta mv. Now, therefore, impulse can be defined as the change in momentum or the product of force and times. The area under a force-time graph is the impulse. Work, power, and efficiency. I'll try my best to upload, guys, some very good notes for elastic and inelastic stuff for the young models as well on the Instagram account. So just try to see it, you know. So, work, power, and efficiency. We have basically the power and the work and the efficiency. Wow. P is equal to FV, while W is equal to Fs cosine theta. P is equal to delta W over delta T, while efficiency is equal to useful output power over input power. And, yeah. So, there are many types of energy. The gravitational potential, kinetic, chemical, elastic potential, electrical, sound, and more. Work is done when a force is applied across a distance. Energy is measured in joules and power is measured in watts, where 1 watt is equal to 1 joule per second. Now we go to the density, but before we do the density, where will we go? We will come here. Lovely. Momentum. Momentum is equal to mass times velocity. P equal mv. The conservation of linear momentum we talked about, and the elastic and inelastic, etc. Force as the rate of change of momentum is this, impulse is that, etc. and another more time, etc. Here we have the work, energy, and power. Energy transfer, W is equal to Fs cosine theta, where theta is the angle between F and S. Significance of the area under a force displacement graph. Power is equal to rate of doing work, which is equal to rate of energy transfer, which is equal to delta W over delta T, which is equal to Fv. The quantitative questions may be set on variable forces. The efficiency can be calculated using useful output power over input power. Efficiency may be expressed as a percentage, so you time by 100. Conservation of energy, the principle of conservation of energy, basically the Potential energy is calculated as mg delta h, while the kinetic energy is calculated as half mv squared. The quantitative and qualitative application of energy conservation to examples involving gravitational potential energy, kinetic energy, elastic potential energy, and work done against resistive forces. Now we have the bulk properties of solids, and the Young modulus will be at the very end, but like we're almost there. Just want to highlight something, guys. This is a key points revision thing. It's not like it's a deep revision, but not that deep. Like, for example, we haven't explained much about the proofs. We haven't explained much about the efficiency, the elastic collisions, etc. I said I'm gonna post notes, but like we haven't explained that, and it's important. So like, you can go watch it if you need deep revision about it. We just talked about it, like, as fast. So the density, again, here, it's equal to m over v, which is mass over volume, and it has kilogram meter to the power of -3. Density is the mass of a material per unit volume. To find the density of a liquid, its mass and volume can be measured. To find the density of a solid, its mass can be measured as normal, and then its volume by measuring the volume of water it displaces. Hooke's law says that the force applied is directly proportional to the extension. So force is equal to K delta L. Force is equal to spring constant times change in length. The limit of proportionality is the point beyond which Hooke's law no longer applies. The elastic limit is the maximum stress that can be applied without permanent plastic deformation, which is when it turn into its original shape. The elastic deformation is the material returns to original shape and has no permanent extension. Energy stored as elastic strain energy, for example, an elastic band. But the plastic deformation, the material is permanently stretched because the atoms have physically moved relative to one another. Energy is used to deform it, for example, polyethylene. Now I have the stress and strain. Tensile stress is the force applied per unit cross-sectional area, measured in Pascal or Newton meter to the power of -2. Tensile strain is the extension per unit original length and has no unit. For example, stress is equal to F over A and strain is equal to delta L over L. And so it does not have units, as you see, because M over M, 0. If enough stress is applied to a material, and you can make sure of this as well. If enough stress is applied to a material, it can fracture. This is called the breaking stress. The maximum stress it can withhold is called the ultimate tensile stress. A brittle material fractures without showing any plastic behavior. A ductile material can be stretched into long wires and stay permanently stretched. The strength of a material is its ultimate tensile strength. Now the energy stored. If Hooke's law is obeyed, energy stored in the area under the graph. So work done is equal to half F delta L, but work done is equal energy stored. So energy is equal to half F delta L. So E is equal to half K delta L square. So basically work done is equal to half K L square. So the energy in a spring can be transformed into kinetic and gravitational potential energy. Lastly, the Young models, which you will have good notes, inshallah, on the Instagram. Just go check it from there if you want to. Basically, it's the up to the limit of proportionality, which means the stress and strain are directly proportional to each other. If you divide stress by strain, you get the Young modulus, a constant measure of stiffness. Young modulus is equal to tensile strength, which is over tensile strain, which is equal to FL over A delta L. The gradient of a stress strain graph is the Young modulus. The area under the graph is the strain energy per unit volume, and therefore energy per unit volume is equal to half times stress times strain. And this is the end of our video, guys. Yep, we're done. I know we have done half. Guys, why am I always opening this PDF? I know January 2025 great boundaries are such a nightmare. For real, like, I'm not sure if you know the other great boundaries, but I'll show you a random one. Like, one of the most recent as well. Oh, no, that's not. Here, June 2023. Like, not that old, bro. And look, physics, Unit 1 was 51. Like, it was something between the 51s, 51, 42, 52, 54, 47. Unit 5 was 47, guys. 47, okay? And then here, it's 59. 12 more marks. I'm afraid. I'm actually afraid. No, please. Okay. I'm scared, not afraid. Whatever. So let's go. So this is the end of our video. Supposedly we went through anything, like all of the stuff. So yeah, of the last lessons, if you want any extra detailed notes, you'll find also in PMT. This is not an advertisement, guys. Okay, so 3.3 as the chapter we'll be covering next video, inshallah. It's about particles, radiation, and radioactivity. And when we finish this chapter, we will be done with the first unit. Guys, should I just take it now? It's not that big to leave, like I'd say. Unit 1, full revision. I better do that, right? Guys, but I did an outro. Okay, I'll have no, I can't. Unfortunately, I have a class after, like, at 6. Okay, I'll say it's a unit 1 thing. I'm just gonna say it. But here you guys are the notes if you'd like to study, and then it's a unit 1 thing. Write me in the comments. Have a nice day. Bye.